Hola chicos. Hoy tenemos una lección muy fácil. ¿Quién puede traducir? ¿Quién puede traducir mis palabras? Yo dije que hoy nosotros tenemos una lección muy fácil. ¿Quién puede traducir? Pienso que nunca puede traducir. Gracias. Es verdad. Empezamos. Let me focus my camera. Okay. Hello, everyone. Happy Friday. As I said in Spanish just a moment ago, and as was typed in the chat, we have a pretty easy lesson today. This is going to be a lesson where, again, the quiz was originally going to be one lesson and one quiz, but I'm splitting it up into one quiz over 2 days. So you're going to be able to do 3 of the 6 questions in today's quiz after this lesson. Okay? All right, so let's begin. So let me just do a little review. All right. So far, when we've been talking about rotational dynamics, we've learned about 2 things. We've learned about torque, which is denoted by tau, and it's equal to F perp times R. And torque is a twisting force. So it's something that causes a twist, okay? Then we learned about something called rotational inertia, which is denoted by I, and it's the sum of mr squared. And it's basically how difficult it is to start and stop, okay? Rotations. All right. So that's what we've learned about so far. Now it turns out that there is an analogy between linear motion and rotational motion. Okay, so there's actually a pretty close analogy. Okay, so let's talk about that analogy a little bit, and we're going to fill out this analogy even more as part of this lesson today. So so we have linear motion, and then we have rotational motion. So in linear motion, we have a force, F, which a force is a push or a pull that makes something move linearly. It makes something go from point A to point B. Does anyone want to take a guess? What is analogous to a force when we're talking about rotational motion? So a force makes something move linearly from point A to point B. What makes something rotate? Type it into the chat if you know. Espero sus respuestas. It's not force. Okay, I will. It is torque. So a force makes something move from point A to point B. A torque makes something rotate. All right? So they're analogous, except one is talking about linear motion, the other one is talking about rotational motion. Okay? Mass, M, determines how difficult it is to get something moving from point A to point B. What is the quantity that determines how difficult it is to rotate it between different angles? Type it into the chat if you know. Mass determines how difficult it is to go from one location to another location, to get something started moving. What physical quantity determines how difficult it is to get it started rotating? Esperaré sus respuestas. Okay, I don't think anyone feels like talking today. So the analog of mass is inertia. Oh, exactly. Thank you for typing that in. Inertia, I, is the analog of mass. So when we're talking about linear rotation, we have force and mass. When we're talking about rotational motion, we have torque and inertia. So we talked about, so what are some other linear quantities that we talked about? We talked about displacement, okay, which was delta x. We talked about velocity, which is v, and we talked about acceleration, which is a. And so the topic of today's lesson is the rotational version of these three quantities. Okay? And so today's lesson is about what's called angular kinematics. Okay? Angular kinematics. So, let's suppose we have an object. So maybe it's a, I don't know, a beam. Okay? And the beam goes from horizontal to I don't know, it rotates by some amount. Okay, like that. So now it has a certain angle. Okay, here it has an angle of 0. Here it has an angle that's roughly 45 degrees. Okay, so theta is called the angular position. Okay, it's the angular position. All right. So the units, you can use lots of different units for angular position. Okay, you could use radians. You could use degrees. And this is actually the only part of the class where we will use radians. Okay, we will use radians to describe angular position. Okay, you can use degrees, but it turns out that it's going to be easier to, and I'll explain why in the next lesson, but it's going to be easier to use radians when we're talking about angular kinematics. Okay, so that's angular position. Now there is delta theta, which is your final angle minus your initial angle, and that is called the angular displacement. Okay, that's called the angular displacement. So let's do an example. Okay, what is the angular displacement if you have a rod that's pointed in this direction, okay, and then it rotates over to here, and this is supposed to be a 45-degree angle, okay? So it rotates from here to here. This is the starting point, this is the ending point. All right. So if we think about this, it rotated basically 3/4 of a half circle. Okay. So remember, half a circle is pi radians. So 3/4 of that is 3 pi over 4 radians. So it goes 3 pi over 4 radians in the clockwise sense. So this would be a delta theta of negative 3 pi over 4 radians. It would be the delta theta there. Okay? So that's angular displacement. So if just like with torques, if angular displacements are in the clockwise sense, that is negative, and if they're in the counterclockwise sense, that is positive. Okay. What if you have something that goes from here and it goes, and now it's oriented in this direction? What would be the angular displacement in that case? I'll wait for a response. While I'm waiting for a response, angular displacement, sometimes the units of angular displacement are, another unit of angular displacement is revolutions. So one revolution is a full circle. Okay, so you also could use revolutions. So 2 pi radians is equal to 360 degrees, which is equal to 1 revolution. Okay. All right, no one wanted to answer that. So this is half a circle in the clockwise sense, or in the counterclockwise sense. So that would be plus pi radians is that angular displacement. Okay. So that is angular displacement. Now, there's another quantity. Oh, excellent. Someone typed it in. So there's another quantity, which is the rate of change of angular position. Okay, and that's the change in angle divided by the change in time. Okay, so basically what this is how fast you're spinning. Okay, and that is called the angular velocity. Angular velocity. And so angular velocity is denoted by omega. This is not a W, okay? It's the Greek letter omega. So it's kind of like a W, but it's rounded a little bit more, okay? So this is the Greek letter omega. It's so this is a lowercase omega. You probably know the uppercase omega is this one. Okay. So this is an important definition. That's called the angular velocity. So it's how fast you're spinning. The units of angular velocity, just like the units of regular velocity are meters per second, the units of angular velocity are radians per second. Okay. So that's important. There are some other common units of angular velocity. There is, who can tell me, now I'll go to this one next, but who can tell me the unit of angular velocity that is commonly used in the automotive industry? Okay, it's right on your dashboard. If you're driving a car, you actually have it right on, you can see what the angular velocity of the drive shaft of your engine is. Okay, who can tell me what that unit is? But some other common units are degrees per second. Okay, so let's do a little example. RPM, excellent. Revolutions per minute, that's an angular displacement per time. So RPM is a unit of angular velocity. So what they're telling you is what is the angular velocity of the drive shaft, because you're you know, the engine in your car is rotating the drive shaft really fast, and then that rotation of the drive shaft is translated through, it's transmitted with the transmission through a bunch of gears to the rotation of the wheels of your car. Okay, it's important to keep in mind that the RPM of the drive shaft of your engine is not equal to the RPM of your wheels because of these gears. There's a gearing ratio that changes that. Okay, so let's suppose that an object does 8 clockwise rotations in 3 seconds. What is the average angular velocity? Okay, so 8 rotations. So that means, so we have delta theta over delta t. Okay, 8 rotations in the clockwise sense is going to be an angular displacement of -8 times 2 pi. Okay, because remember, one full rotation in radians is 2 pi, and we have 8 full rotations in the clockwise sense, so that's why it's -8 times 2 pi. In 3 seconds, so that would mean your angular velocity is about -16.8 radians per second. Okay? So there you have it. Then, the next quantity we'll learn about is the rate of change of angular velocity. All right? Type it into the chat if you can take a guess at what the rate of change of angular velocity is called. Okay? So if I wanted to describe it, I would say it is, in another way, I would say it's how fast you spin faster. Okay? So the rate of change of angular velocity would be change in angular velocity divided by change in time. Okay? And that's denoted by the Greek letter alpha. So alpha looks like an A, but it's kind of more fishy looking. And that stands for what is called, excellent, yeah. It is the angular acceleration. Okay, so that is the angular acceleration. Type it into the chat if you think you know what are the units of angular acceleration. Okay, what are the units of angular acceleration? And while I wait for a response to that question, we can actually complete this analogy. All right, so when we're talking about rotational motion, we have the angular displacement, which is denoted by delta theta. We have the angular velocity, which is denoted by omega, and we have the angular acceleration, which is denoted by alpha. So if you are solving a problem or if you are discussing some physics and you need to differentiate between these two, you can call this the linear displacement, the linear velocity, and the linear acceleration. Okay, so that's how you would differentiate between the two. Okay, if it was obvious that you were talking about rotational motion, you could just say acceleration. You don't have to say angular acceleration, but if you're doing a problem maybe where something is rotating and it's translating, so it's going from point A to point B while it's rotating, then you have both an angular velocity and a linear velocity, so then it's important to differentiate between the two. Okay. All right, no one answered. The units of angular acceleration are radians per second squared, just like the units of linear acceleration are meters per second squared. Okay. You could also use degrees per second squared in some cases. No one uses this unit, but I think it would be funny to use the unit RPM/PM. That would be revolutions per minute per minute. Don't use that. No one would know what you're talking about. Okay? So that's called angular acceleration. So you might recall that, so I'm going to, the rest of the piece of paper, I'm going to divide it in two. And I have linear motion and I have rotational motion. Okay, so you might recall, okay, that we discussed the equations of kinematics, the kinematics equations. And those equations were, if the linear acceleration is equal to a constant, we had three equations that we used. They were delta x equals v naught t plus 1/2 a t squared. Okay, we had v final equals v initial plus at, and then we had v final squared equals v initial squared plus 2a delta x. Okay. In rotational motion, we have, if alpha is equal to a constant, so the angular acceleration is constant, then we have three equations of angular kinematics, which are the exact same as these equations. The only difference is, okay, that we replace each variable by its angular version. Okay, so we have delta theta equals, and then what's analogous to velocity is angular velocity, which is omega. So initial angular velocity times time. Time is the same. Okay, there's no angular time. It's just time. Plus 1/2, and then linear acceleration, the analog is angular acceleration times t squared. So it's the same idea between these two equations. It's just this is the angular version of it. Then we have v final equals v initial plus at. This is going to become omega final equals omega initial plus alpha t. And then v final squared equals v initial squared plus 2a delta x becomes omega final squared equals omega initial squared plus 2 alpha delta theta. Okay? And you use these equations in the exact same way that you used the kinematics equations that we learned at the very beginning of the course. Okay? And so for that reason, I'm not really going to do any examples. I'm just going to let you guys figure it out for yourselves. There is one other thing. We could even talk about graphs. of linear motion. Okay? If you have a position time graph, the slope of that position time graph is velocity. If you have an angular position versus time graph, the slope is angular velocity. If you have a linear velocity time graph, then to have a positive linear velocity means you're going to the right. To have a negative linear velocity means you're going to the left. If we had a graph of angular velocity versus time, a positive angular velocity means you're spinning counterclockwise. A negative angular velocity means you're spinning clockwise. Furthermore, the slope of that graph of a velocity time graph is your linear acceleration. The slope of an angular velocity time graph is your angular acceleration. The area under the curve of a linear velocity graph was linear displacement. The area under the curve of an angular velocity graph is angular displacement. So it's completely analogous. Okay? And that's the reason why I'm not really doing any examples. We're just talking about this theoretically from a high level. Okay? So that is my lesson. I hope you found that it was easy. And so I'll meet you in the Zoom room, and I'll let you know which of the problems you know how to do already in the quiz. Okay?